Hello everyone, my name is Changpeng Xiao. Today I will introduce a recent work with Ashimo Nara. It is about quantum and classical query complexities of functions and matrices. As you may know, quantum linear algebra plays a very important role in the exploration of quantum advantages. For example, the Hamiltonian simulation problem, in the language of quantum linear algebra, we try to compute the exponential function of e to the iat. Here, I is the imaginary unit and A is a Hermitian matrix. This is a fundamentally important problem in quantum computing. Another important problem is the linear system problem. In this problem, we try to compute A inverse times a quantum state B. And the first algorithm to solve this problem is the HHL algorithm. This algorithm greatly promoted the development of quantum linear algebra. I mean, there are wide applications of this algorithm in many areas. For example, in quantum machine learning, such as quantum algorithm for the recommendation system problem. In this problem, we try to prepare the quantum state of the ith column of a truncated matrix of A. And also in the problem of solving linear differential equations, we try to compute this kind of exponential function. And all these problems can be described as functions of matrices. That is, we try to prepare FA times a quantum state B. And this problem can be solved by a similar idea to the HHR, but it can also be solved more efficiently by a more advanced quantum technique called quantum singular value transform. Okay, now I will briefly introduce this quantum singular value transform. For simplicity, I'll assume A is Hermitian and with the bounded operator norm. We are given a unitary of this form. The top left column is A, and F is bounded by one polynomial of degree D. Then there is a quantum circuit that implements a unitary of this form. This top left column is FA, and this quantum circuit uses U inverse, and the controlled forms of U and U inverse, or the D times. So as a direct result, we can just apply this unitary to a state and obtain this quantum state. Of course, this idea still works if F is not a polynomial, since we can just find a polynomial approximation of F. Indeed, for functions and matrices, if we apply QSVT, usually we will obtain optimal quantum algorithms. So it is interesting to know how about this in the general case. And also, the functions and matrices are very important in quantum computing. So it is also very interesting to know what is the separation between quantum and classical computing for functions and matrices. So to resolve these two questions, we consider the following weaker problem. In this problem, we are given a function from -1, 1 to -1, 1. And we assume A is a sparse and Hermitian matrix with bounded operator norm. I and J are two indices, and the epsilon is the accuracy. The goal is try to compute the IGS entry of FA up to some error. The complexity we care about here is the query complexity. A is a sparse matrix, so usually we are given two oracles in the standard way. The first oracle tells us information about the sparsity. If the input is IJ, then it outputs PIJ. Here, PIJ is the index of the just non-zero entry in the ith row. The second oracle is just the query the entry of IJ. So the query complexity is the minimum number of calls to the oracle to solve this problem. Okay, next, let's see a very simple example, the matrix powers. First, we will consider the classical case. A is a sparse, this is our assumption. So using the definition, we will know the IGS entry of A to the D has this kind of formula. Since A is sparse, so each sum contains at most S terms. So in total, there are at most S to the D-1 terms, and this is the complexity. Indeed, we can do better than this, because for XD, we can find a polynomial approximation, and the degree is just the square root of D. So as we can do, compute the IGS entry of a monomial, we can also compute entry of a polynomial of A. And so the complexity can be reduced to S to the square root of D. It is interesting in this problem just matrix powers, is BQP complete. That is, we believe it is hard for classical computers. But how hard it is for a classical computer. And indeed, we proved a lower bound of this form. It is still exponentially hard. It is expansion in square root of D. And in the quantum case, we can just use the quantum singular value transform, and the complexity is linear in the square root of D. So by comparing these two bounds, we can see the quantum and classical separation is exponential, just from the point of square root of D. We also proved a lower bound in this case. It is the square root of D. So from these two results, we can see the quantum algorithm is optimal from the viewpoint of square root of D. And in the general case, we have a similar result. If here we assume F is continuous and A is sparse information, then compute an entry of FA up to some error. The complexity is summarized by this table. Here, this D is approximate degree. That is, for any continuous function, we can always find a polynomial to approximate. And here we hope the degree of G is as small as possible. So in the quantum case, the upper bound is obtained by quantum singular value transform. It is SD divided by some epsilon. And we proved a lower bound, it is square root of D. It is linear, it is D, sorry. Classically, we have a very naive quantum classical algorithm, and we proved a lower bound, it is always exponential in D. So this quantum lower bound is very similar to the famous polynomial method for Boolean functions. Okay, next I will explain how we obtained this table. This is our key theorem. In this theorem, f is a continuous function, and f are the odd and even parts, f odd and f even. Then we can find a symmetric tridiagonal matrix of this form, such that the operator norm is bounded by 1. And the nth entry of FA is epsilon. And more importantly, the dimension of this matrix A is the approximate degree of the odd part plus a constant. Yeah, we have a similar result for the even part. Yeah, I will not introduce the proof of this theorem, but basically it uses these three techniques: the linear semi-infinite program, the dual polynomial method, and some properties of tridiagonal matrices. Yeah, this theorem basically builds a connection between symmetric tridiagonal matrix and the approximate degree. Okay, now next I will assume this theorem is correct and try to prove the lower bounds in the quantum case and also in the classical case. When we try to prove a lower bound, usually we will build a connection between the problem we care about and some knowing hard problems. In the quantum case, the problem we will use is the parity problem. We are given x1 and xn, they are 0 or 1. Our goal is to compute the bit sum of xm. And it was proved that the quantum query complexity of parity problem is odd n. So to build a connection between parity problem and the function of matrices, we will consider the adjacency matrix of a graph. So we will build a graph. Here we consider a weighted graph. The vertices are I and t. Here I is from 0, 1 to n, and t are 0 and 1. The edges, there is an edge between I minus 1t and I and t plus xi. Yeah, we will determine the weights later. So before that, let's see what this graph looks like. For example, if suppose x1, x2, x3, x4 are 0, 1, 1, 0, then G has this kind of structure. There are two levels of nodes, and this connection are totally determined by the input x. So for example, x1 is 0, so there are two horizontal edges, and x2 is 1, so there is a cross connection, and x3 is 1, there is another cross, and x4 is 0, so there are two horizontal edges. So basically, there are two cases in this graph. and they are disjoint from each other. So in the general case, the two places have this kind of form, 0, 0, 1, x1, 2, x1 plus x2, and the last one is n, x1 plus xn. Okay, here A is the adjacency matrix of G. So since the adjacency matrix of a triad of our path is just a symmetrical tridiagonal matrix, symmetrical tridiagonal matrix. So A is basically two symmetrical tridiagonal matrices. If we order the vertices in some nice order, then it's just the block form. So, okay, let's consider the problem. In the first case, if the sum of them is 0, then as you can see, 0, 0 and n0 are connected. 0, 1 and n1 are connected. So 0, 0 and n1, they are not in the same path. So this quantity is always 0. In the second case, if this is 1, then they are in the same path. And we hope we can find some weights such that this quantity is far from 0. And here the weights are determined by our K0 because it is a symmetrical tridiagonal matrix. So as a result, if we can estimate this quantity, then we can solve the parity problem. But the parity problem is hard, so we will obtain the claimed lower bound. And here it is very important to make sure that this n is close to the approximate degree. And this idea is indeed inspired by the no fast forwarding theorem. In the classical case, we will consider this correlation problem proposed by Ellison and M. Banis in 2015. This problem greatly separates classical and quantum computing. In this problem, we are given two Boolean functions, G1 and G2. Di is just like the diagonal matrix of Gi. H is a Harman operator. So we are care about this quantity, phi, G1 and G2. Yeah, it has this kind of formula. Basically, it is the correlation between G1 and the Fourier transform of G2. And our goal is just to approximate this quantity up to a constant accuracy. And it was proved by Ellison and Banis. For this problem, the classical complexity is low bounded by square root of 2 to the n divided by n, while the quantum complexity is just all 1. Okay, we will use this problem. So to build a connection between this problem and the function of matrices, we will consider the Feynman's clock construction. Here, let's say U is any unitary operator. We consider this kind of Hermitian matrix A. So if psi t is t, answer ut, u1, and apply to 0, here t means the time. So if we apply A to this psi t, it is a linear combination of psi t minus 1 and psi t plus 1. So this is something like a random walk on a line. So this means we move forward, and this means we move back. So in this subspace, A is a symmetrical tridiagonal matrix. Okay, this is a construction we will use. Next, let's come back to the correlation problem. In this problem, we have a unitary of this form, and we will obtain a matrix A, Hermitian matrix A, by Feynman's clock construction. Here, to make sure A is sparse, we decompose this tensor product of H into, let's say, n parts. So each part is 2 sparse. As a result, there are 3n plus 2 unitaries in this decomposition. The initial state is 0 tensor 0, and the ending state is n minus 1 tensor, this whole operator u applied to 0. In the problem we care about, we try to approximate an entry of Fa. And this psi 0 is just one computational basis. We consider another computation basis. This is related to this phi n minus 1. We call it phi, this is psi n minus 1, this is phi n minus 1. So we consider this entry of Fa. It is not very hard to compute that this entry equals the product of these two terms. And this is a quantity in the correlation problem, and we know it is hard to compute. But this one is easy because in this subspace of this size 0 and size -1. This matrix A is a very small matrix. The size of the matrix is the capital N, which has order little n. So this quantity is easy to compute. But this one, it is an entry of FA. So as a result, we will know that this is hard to compute. Yeah, this is our idea to prove a classical law bound. Okay, finally, I'll make a simple conclusion. For functions or matrices, we obtained this table about the curve complexity. And from the point of the approximate degree D, the quantum algorithm is optimal. And we also obtained that the quantum classical separation is exponential. And there are also some interesting open questions. For example, in our work, we didn't consider the dependence on epsilon. It might be just a 1 epsilon because of the aptitude estimation, but we are not sure how to prove this. And I think another interesting question may be, since this law bound is very similar to the famous polynomial method, which is very useful in the proof of law bounds. So it is interesting to know some similar results about in the proof of law bounds. Okay, thanks very much for your time.